Hey there, this is our mixed ANOVA and SPSS walkthrough. All of the resources for this walkthrough can be found on Canvas in the mixed ANOVA module down here in the SPSS resources. The demonstration, SPSS demonstration, mixed ANOVA example document here has steps for conducting the analysis in SPSS, conducting the simple main effects analysis, our research example, which we'll go over in a minute, and annotated output. So you can see all of the output, and then I've annotated it on here for you, how you interpret each one of those tables. So we'll go through that in this video here in just a minute. You can find the data set for this mixed ANOVA example right here on Canvas, the syntax file to run the simple main effects analysis here, a write-up of the results from this analysis is here. You can see here's an example of how I write up the results from this analysis, so you can see how that would work. And then here's also some just additional ANOVA, mixed ANOVA outputs and just some kind of comments on them that you might find helpful. You can see right here with some annotated output there as well. So for this example, let's look at the research scenario here. In this example, a researcher is interested in comparing the relative efficacy of a behavior modification approach to dieting versus a behavior modification plus exercise approach on weight loss for a group of overweight men. In this study, we also are including a control group. So in this design, 12 men are randomly assigned to one of the three diet programs, and then weight loss is measured 2 months, 4 months, and 6 months after the program begins. So the data for this analysis is down here. So we can see subject 1 was in the control group who didn't do any type of behavior modification or exercise program. And this was their weight loss at the end of 2 months, their weight loss at the end of 4 months, their weight loss at the end of 6 months. And the weight loss is relative to, so between 4 and 6 months, they lost an additional 3 pounds. You can see the control group had 12 subjects. The behavior modification group here had 12 subjects, and the behavior modification and exercise group had 12 subjects. So our you can see here the between subject factor here is the diet program. So there's 3 levels to this between subject factor, the diet program, whether it's the control group, the behavior modification, or the behavior modification and exercise. And then the within subjects factor is time. So it would be weight loss measured at 2 months, 4 months, and 6 months. So you can see that this is a mixed design because we have a combination of within and between subject factors. This is a pretty simple mixed design. They can get complicated very quickly. So here we have what we would call a 3x3 mixed ANOVA, where 3, because we have 3 levels of our between subject factor and 3 levels of our within subject factor. So the steps to perform this analysis are going to follow pretty closely kind of to what we did with the factorial ANOVA. The first thing we'll do is look at the interaction effect, look at the significance level of the interaction effect. If the interaction effect is not significant, then we're going to interpret the main effects for our between subject and within subject variable. And for that, you could just follow like the same guidelines as in like one-way ANOVA for the between subjects variable and for the repeated analysis for the within subjects variable. Now, if there is a significant interaction effect, similar to what we did in the factorial design, is we're going to conduct a simple effects analysis. And so here we could conduct a simple effects analysis for both, in this example, I'll conduct it for both the within subject factor and the between subjects factor. So for the within subjects factor, we would examine the 3 DAC programs by conducting a one-way repeated measures ANOVA for each program, looking at the influence of time on weight loss. The simple main effects analysis for the between subject factor, we would basically do a one-way between subjects ANOVA, looking at each of the 3 DIET programs at each time interval. So we'd select on time interval, essentially, look at time 1 and say, is there a difference between the DIET programs? And we'll talk about that as we go through the analysis. So you can follow along with what I'm doing in this document. I'm going to move over to SPSS just to give you a demonstration of how it's done here. You can see here's the example syntax file. So I give you the syntax for running the one between, one within, 3x3 ANOVA. You could just highlight this and hit play here and it'll run it. Or, now one thing I should talk about first before we actually run the analysis is make sure you notice how the data are entered into SPSS. Remember, each row in SPSS represents an individual in our study or a subject in our study. And then each column represents a variable. So our between subjects variable diet has 3 levels. So I think we have 1 is for control group, 2 is for behavior modification, and 3 is for behavior modification and exercise group. And then our within subjects factor has 3 levels, so it gets 3 columns in the data set because it represents weight loss at time 1, weight loss at time 2, and weight loss at time 3. So just make sure you notice how the data are entered into SPSS, so you'll do that on your own for the assignment. So to run this analysis, it's very similar to the repeated measures analysis. It's analyze, general linear model, repeated measures. We'll click on it. We have to name our repeated measures or within subject variable. I'm just going to call it time. We need to say the number of levels. It has 3 levels. We'll add it. If we had any more within subject variables, we'd add them here. We would click on define. We need to tell SPSS, well, what are those 3 within subject variables? And here they are. We named them weight loss 1, 2, and 3. And then diet here is a between subjects factor. Bring it over here to the between subjects factor. We can get a plot if we want to see a visual of an interaction effect. We're going to put time on the horizontal axis and look at graph separate lines for the different DIET programs. We'll do a line chart for here is appropriate. And I always like to start the y-axis at 0 so it doesn't, you get actual differences. It doesn't insinuate the differences between the points. Like sometimes it'll just zoom in right on it or make the differences look bigger than they actually are. If you start the y-axis at 0, it doesn't do that. The post hoc test would be if we needed a post hoc test for our between subjects factor. I'm going to hold off on that because we're not going to interpret it. Remember, if we have a significant interaction effect. For the estimated marginal means, we'll grab all three of these and bring them over. I'm not going to compare the main effects just now. We could use that if we don't have a significant interaction effect. And then we'll go over here to options. I'll get some descriptive statistics, estimates of effect size, and my homogeneity test. I think that's all we want there. And let's say okay. All right, so first there we go. It gives us the syntax we need to create this. This should be the same thing that is I have in my syntax file here, pretty similar. You get your within subjects factor variable. A lot of the stuff is just to check, make sure your data were entered correctly. You had 12 subjects in each diet program. That was right. If you noticed a mistake there, like one had 13, one had 11, you miscoded somebody. So it's good to look at some of these descriptive statistics just to make sure things are being coded correctly. The first thing we see after the descriptive statistics is this boxes test of equality of covariance matrices. And so this test tests that assumption, that homogeneity of covariance matrix assumption, basically that the covariance matrices of the dependent variables are equal across groups. And this is another one of those tests we want to fail to reject the null hypothesis, because the null hypothesis is that we're meeting the assumption that the covariances are equal. And so if we look at the significance value of boxes F test here, we see that we are meeting the assumption, so that the covariances are equal across the groups. In this case, violating the assumption wouldn't be too severe because we have equal sample sizes in each of the groups. Same thing with the homogeneity of variance test later on. It's not going to be as big of a deal if we violate or not because of the equal sample sizes. We're going to ignore the multivariate test box. We could look at the test of sphericity here. We look at the significance level of Monty's chi-squared statistic, and we see that this is saying that we do violate the sphericity assumption. Because again, the null hypothesis here is that there are equal variances and covariances among the repeated measures. And here there's a violation of it. It's not a big problem because we're going to then use the greenhouse geyser adjusted test. Remember, there are other citations I gave you where some people just ignore this test completely and always use the greenhouse geyser reported line. So here we have evidence that we really need to do that. So we're going to go down to our test of within subjects effect. So this will give us our repeated measures variable, the main effect for it, and our interaction term. So you can see the interaction term here. Remember, SPSS represents those with a product. So the interaction between time and diet. We'll look at the greenhouse geyser adjusted line. And we see that there is a significant interaction between time and diet. So this significant interaction is really telling us that that weight loss across time depends on what diet program we're in. And we'll see that when we look at the plot down below. Let's go look at that. We're going to scroll on down here to the plot. We can see, looking at the plot, remember non-parallel lines are an indication of an interaction effect. And, you know, you can see like diet 1 and 2, the lines are pretty parallel, but diet 3, you can see it's especially this point here seems to make it at time 2. You know, those at time 1, no matter which weight program, which diet program you're in, everybody seemed to be losing a good bit amount of weight, between about 4.5 and 6 pounds. However, at time 2, it was really only diet 3 that people continued to lose just as much weight as they did. You see in diet 1 and 2, weight loss decreased for them. So instead of losing around 4.5, 5.5 pounds, they were only losing around 3.5 and 4 pounds. Whereas in diet 3, they continued to lose roughly the same amount as they lost in the first time period. And then you can see in time 3, weight loss drops off for everybody. So that's kind of what's going on with this interaction effect. So you can see that the amount of weight loss, the amount of weight loss over time depended on which diet program you were in. That's what the interaction effect is telling us. So that's where we saw the significant interaction effect. Since the interaction effect is significant, we're going to ignore the main effects and interpret and run a simple effects analysis. We'd be interested in this table if we were really interested in like the trend in the change over time. If that was an interest to us, we can see what kind of trend was occurring over time. Here's the Levine test. So this is the homogeneity of variance test box. So it gives us our different, you know, whether the variances among the different diet programs were equal at each time frame. You can see at time 1, it looks like we're violating this assumption, but at time 2 and time 3, the variances seem to be equal. We're not really worried about violating it in this instance because we have the equal sample sizes in each of our groups. If we didn't have equal sample sizes in our groups, we may have to make some type of adjustment to account for this. Violation. We could either, you know, mention it in the write-up, use a more stringent alpha level, or if we're very concerned about it, we might have to just change the type of test that we're doing. The between subject space box, this would have the main effect for diet here. You can see that the diets were significantly different, averaging over time. So really this test is comparing these means to be the average weight loss for each diet program averaging over the 3 time periods. However, we saw as the interaction, the amount of weight loss over time depended on which diet program you were in. Same thing, this is the main effects for time. So this would be the amount of weight loss at each time frame, ignoring which diet program you were in. And then this gives us the cell means that we're graphing below here. So diet 1, time 1 is a 4.5. Let's see, diet 1 is blue, time 1's here, that's about 4.5. So these are the different cell means that we're graphing here. So since we found a significant interaction effect, our next step is to run the simple main effects analysis. And we're going to do that similar way we did in the factorial, but we're going to have to use the SPSS syntax to actually get this to run. You can't do it through the drop-down menu. So let me show you how to do that. So we run the simple effects analysis. If we need to get the syntax generated, we can go back to Analyze, general linear model, repeated measures, click define, and then just tell it to paste that syntax. If you don't have a syntax window open, one will open automatically for you. You can see, so this was the syntax that was generated. We need to modify this line right here. And we're adding basically the same thing we did in the, for the factorial design. We want to, here we want to compare just where we want to compare which variable we want to compare over levels of the other variable and what type of adjustment we want to make. If you look at my SPSS syntax file, I try to annotate this for you. You know, here's the syntax, just the basic descriptive syntax. Here's the simple effects analysis for the within subject factor. So that's the factor we're putting in the compare. We want to compare time at each level of, at each DAT program. Here's an alternative way you can do that where it doesn't pull the error term across analyses. And here's a simple effects analysis for the between subject factor. You're basically putting the between subject factor in the compare box too. You know, yours is going to come out like this, and then we would just, depending on which one we wanted, you could add it here. I think you can actually, let's test this out. This is fun testing it while I'm making the video. I think you can request both of them at the same time. Let's just try it out and see. Okay, yeah, it looked like it worked. Didn't give us any errors. So most of the syntax here is the same that we had before. There's our descriptive statistics, the boxes test, the sphericity test. Here's our, you know, interaction effect. It's still on there. There's the quality of variance test. Here's our marginal means. Okay, and then here where we have our, you know, we're starting to give your estimated marginal mean, so your main effect means for DAT and time, the cell means for the interaction effect. Here's where it's going to start putting the simple effects analysis. So here are pairwise comparisons comparing each time within each DAT program. So for DAT program 1, how does time 1 versus time 2 compare, time 1 versus time 3? And then here it is again. So that would be your within subjects simple effects analysis. And here is then your between subject simple effects analysis. Here we're comparing each diet for each time frame. So let's go back up and talk about this one. SPSS for some reason doesn't give, it gives you the multivariate test for the repeated measures part. So we can just ignore that since we're not doing the ANOVA part. So essentially what's happening here is we're selecting on each DAT program, and then we're running a one-way between subject, or sorry, a one-way within subjects ANOVA, so repeated measures analysis across the 3 different time points, right? So for diet 1, so for those in the control group, is there a difference in weight loss between time 1 and time 2? And this is saying there's not. Is there a difference in weight loss between time 1 and time 3? It's saying there is. Is there a difference in weight loss between time 2 and time 3? And it's saying there is. So it's looking at, So that one, so it's comparing this mean to this one, this mean to that one, and this mean to that one. So saying these aren't different, these are different, and these are different. That's what. So we have the same thing here. So for diet 2, the behavior modification approach, there is a significant difference between time 1 and time 2, and between time 1 and time 3, and between time 2 and time 3. Same thing with diet 3. There's no difference between time 1 and time 2, which is kind of what we saw in that graph. Remember that weight loss was essentially the same for diet 3 at time 1 and time 2. That was the only one who had essentially the same amount of weight loss. There is a difference between time 1 and 3, and same thing with 2 and 3. Remember, there's that big drop off at the 3rd time period. Here is the simple effects analysis for the between subject factor. So here what we're doing is we're running like separate one-way ANOVAs for each time period. So we're looking just at time period 1 and how do the 3 diets compare. Looking at just time period 2, how do the 3 diets compare? Looking at just time period 3, how do the 3 diets compare? So in this analysis, we're comparing these means here at time 1. We're selecting at time 2 and comparing these 3 means, and looking at time 3 and comparing those 3 means. Here are one-way ANOVA results. We can see that at time 1, the 3 diet programs are essentially the same. Weight loss for the 3 programs are essentially the same. Same thing at time 3. Weight loss for the 3 programs are essentially the same. It's at time 2 that the weight loss for the 3 programs differs. And I bet you can tell what's going on there already. So here we just have to look at, here at time 2, there's no difference between diet program 1 and 2, so the control group and the behavior modification group, but there is a difference between the control group and the behavior modification and exercise group. Same thing, there is a difference in weight loss at time 2 between the behavior modification and exercise and the behavior modification group. That's what these Bonferroni, these are essentially t-tests between each one of them with the Bonferroni correction for the p-values. And so that's saying that these means are statistically different. These aren't, and these aren't. So that is a quick walkthrough of a mixed ANOVA and SPSS. If you look at in my handout here, I also calculated for you, for each of those pairwise differences we found, we could calculate a standardized mean difference or Cohen's d effect size for each one of those. And I believe in the output here, I calculate those for you by hand. You can see, so here they are here. So you'd have those effect size differences. You also have some variance explained effect size differences that you can interpret based on here. So, the interaction between time and diet explained around 24% of the variation in weight loss. How you can interpret those as well. As always, if you have any questions, concerns, shoot me an email or post to the message board. I'll see you next time. Thanks.